All right, everybody. Could I get everyone to sit down? Yeah, we're good to go. We did it. Oh, hey, Robin. Thanks. I'm just going to do a quick intro, and then we'll start with you. But hi, everyone. Thanks for coming out. This is our first in-person lightning talk since the start of the pandemic, at least. So it really means a lot for you guys to come out here today. I also would like to thank Northeastern University for graciously hosting us and dealing with an absurd number of technical issues today. Without them, this meetup would not be possible. Just a round of applause. Northeastern University Vancouver would like to acknowledge that they are located on the unceded territories of the Coast Salish people, including the territories of the Musqueam, Squamish, and Burrard Inlet Nations. We are a volunteer-led, community-focused on improving data science skills within Vancouver and around the world. These talks would not be possible without the volunteers to organize and give talks. We are always looking for speakers and can host talks of any length and will accommodate your busy schedule. This is a great way to get your name out in the community, as well as a great learning experience. Please speak to me or any other organizer after the talks. Along with the talks, there is a bi-weekly reading group. You can sign up through meetup.com. Do you know what the next paper is going to be on?
Next week. I forget. I think next week. Right?
Yes, but what is the paper on? Explainable AI. Yeah. So the next paper will be on explainable AI. Thank you. We also have an online group that discusses data science problems and shares job tips. Please join us from the link on the meetup page and join the hashtag data-science channel. So the way that this is going to work is we have 4 great talks. Each are going to be less than 7 minutes each, and I will be timing it. For those of you who are speaking, I will be making hand signals, except for Robin, you're going to have to do your own timing. And after that, there will be about 10 minutes of Q&A each. I'm going to be monitoring the live stream, so if you have any questions, just feel free to say them in the chat, and I will go ask them for you. I think that's pretty much everything. Oh, one last thing. For those of you in person, I booked the Library Square for after this meetup, so we can all go grab a drink after that. All right, sounds good. Without further ado, Robin, why don't you give it a go?
Hi, thank you, Matthew. Thanks so much for hosting. Can you hear me?
Yeah, how are we doing in the back of the room?
Quiet.
Quiet?
Check.
Keep talking.
Check. And so I'm going to be talking about Vickers' decision for analysis today. How is the sound check going?
We good?
Yeah?
Touch more?
Okay. And check. Yeah, thanks for I can imagine all the technical difficulties today. It must have been a lot to consume. It's bad enough on its own without real life. All right, should I proceed?
Yep, please do.
Great, thanks. So this is about a decision theory-ish type talk. And so previously I gave a talk about binary classifiers evaluating them. This is sort of life cycle that we kind of go through at different. We talked about a few different steps in terms of threshold selection, different ways of doing that, and evaluation. Evaluating outcomes versus predictions.
Hey, sorry, Robin, just one more technical difficulty. You are apparently echoing, so we got to turn off this.
Should I go ahead?
Yeah, go for it.
Okay, today we're talking about utilities. So once we have our predictions and we've made decisions using a threshold.
Sorry again, more technical issues. Okay.
Hi. Oh, Oh, it's good? Okay, great. Okay, so here we're talking about utility, the cost benefit of the outcomes. And so this is about a method that was that came out in 2006 by Dr. Andrew Vickers in a hospital in New York City. So if you had two models that were meant to predict cancer, so which of these two models would we choose to decide who gets a biopsy? So here, imagine model A has an AUC 0.82, model B 0.79. Here's the calibration curve, here's the precision recall curve. Well, I don't know, like, model A looks better, right? Should we choose that? The AUC is higher. You know, the precision recall curve looks a little better. But is either model beneficial? Well, that's what we find out using utility decision tree, and we need to look at the utilities of the different outcomes. And so this method this aspect goes back to 75 with Pocker, and he talks about the net benefit and net cost in terms of benefit to the disease patient and the cost to the non-disease when mistakes are made in diagnosis or there's uncertainty. So here we're really talking about the net benefit, and we have to start looking at the utility of these different cases, outcome cases. And so if we just have these, if we have these predictions from different models and the actual outcomes, that's all we need to produce a decision curve that can show how the different models respond to different cost benefit ratios. And so if we use this method, we don't actually need a perfect calculation of cost and benefit. We get a range of results, and then we can choose where we want to be on that range. So for example, here's one decision curve that's showing model A and model B in blue and purple, and then the simple policy of treat all in this red line. And here is the entire range of 0 to 100% threshold probability, but really the realistic range is in here, and so we zoom into that, and we see that the purple model B actually has better net benefit in the range of interest, of risk range of interest, compared to the other model, A, which in general might look better, but not in the range of interest. So this actually changes our decision of what we would be using in real life to make our decision. And this is showing that using model B would get better net benefit than treating all the patients, regardless of the model predictions. So by adding this decision curve to the set, we can choose, we can better select policies that will be beneficial. So this type of analysis answers questions like, would this model be useful in practice? Which policies are best for patients with different risk preferences? Sensitivity, specificity, AUC, all the usual things that we talk about in evaluating a binary model are just not sufficient to tell us whether it would be helpful in clinical practice. And that's what we're trying to get at here. So one key aspect of understanding how these work is that there's a interplay between, or there's equivalence between the risk threshold and the cost-benefit ratio. And you can see that here. As the cost-benefit ratio means the cost of the treatment versus the benefit of the treatment. So for example, on the far left of the chart is if we imagine that the treatment didn't really have any downside at all. Maybe it was very inexpensive and harmless, and the disease was very bad. That would be over here. And on the other side over here would be a disease that's not that bad, and the treatment is very, very harmful. So you want to be extremely careful when you use it. And so certain situations, medical situations, are going to be in a certain spot in the spectrum, and that's how you know where to look on the x-axis. So there's equivalence between the cost-benefit ratio and the threshold probability, and that's what's shown in this equation. So I kind of isolated the things that confused me at first when learning this method. and I made a list of them here. But the biggest one is just this: the cost and benefit. There are two separate but related relationships that are being shown at the same time between cost and benefit using a DCA. One is the ratio between them, and that's the x-axis. And one is the difference between them, and that is the y-axis. And that was the most confusing point to me at first. So this slide, if you want to understand the method, this slide has all the shortcuts to understand it. And I want to thank Dr. Andrew Vickers and Dr. Karndeep Singh, who's at University of Michigan. They both helped answer questions about the method, and I quoted some of their work here. It was Dr. Vickers who invented it. If you want to learn out more about it, you can go to decisioncurveanalysis.org, and all the papers are listed there. And that's it for me. Yeah, I'm Robin Chauhan. Follow me on, I guess I should have my Mastodon on Twitter. Thanks so much.
All right. So a little bit more technical difficulties on the streaming side of this, but hopefully it should clear up on the next set of talks. But for right now, does anyone have any questions for Robin? I have one sort of immediately, and that is, what got you interested in this type of decision analysis, and do you see it applicable in places that are not in a purely medical context?
Yeah, well, I find it interesting to know what the doctors are doing, because the doctors really care about the real-world impact of their models in a way that many people don't. And so I'm curious to see. I was curious to see what do the biostatisticians do when it comes to making decisions, and what can we learn from that in general about important decisions and decision making under risk. So I've spent some time learning about methods in reinforcement learning, deep RL, very different type of decision making, and this is like a completely the other side of the spectrum. So I wanted to see what I was missing here, and it was very educational.
Payam?
Yell, or do I need to come there?
Yell.
I'll try. I'm not a good yeller. Can you hear me, Robin?
Yeah, kind of, Payam.
Okay, I'll try to be loud. I'm just curious. So as a doctor, so you still need to decide on your risk profile. But I feel like that will be an awkward conversation with a patient who wants to know whether they have cancer or not. If the doctor needs to calibrate their risk profile before giving an answer. How do you deal with this in practice?
I don't have definitely don't have a full answer for you, but I can say that with this, here, let me see if I can. Yeah, with this, can you see this?
Yep.
So on this continuum, I'm more worried about the disease on the left. I'm more worried about the biopsy on the right. First of all, the clinicians will kind of decide that basically for this situation, for this type of disease, for this type of test or whatever, we're in this range, let's say, right? In terms of how risky the disease is versus how risky the treatment is. So they'll kind of start by giving a range, and then depending on the patient, they can adjust more to the left or right. For example, if the patient is very old and is just interested in having the few years left of their life and not being stuck in a hospital, then they might be more to the right, or sorry, to the left. So what I'm saying is, it's easy to adjust with this model, to adjust risk to the left or right depending on the situation. I don't know if that makes sense, Payam.
Yeah, that makes sense. But I guess it's still tricky who makes that decision, right? Like, is it the doctor or is it the patient?
So this method is totally agnostic to that part. I think that's about how they do policies at the hospital and stuff, and I actually don't have much insight into that. But it definitely does. All of this was definitely framed as what is best for the patient, and the cost and the benefit in terms of for the patient, and not necessarily dollars and cents or whatever, but down to what is best for quality of life for the patient.
Awesome, thank you.
So, Xander, you had an area of interest on that graph what drove that choice? Like, why did the clinician want to only look at that part?
Yeah, that's a great question. Thanks for asking that question. So basically, if you go to this part, you'll see. So there's estimating, implicitly estimating cost benefit from clinical policy. That means you can just see what the doctors are already doing. If the doctor's willing to conduct 20 biopsies to find one high-grade cancer as a general policy, then that suggests the implicit probability threshold is around 5%. It's basically just the doctor's current behavior is telling us roughly what regime we're in, and that's how we know. Like the reason this is 20 is because they have some kind of assumption about the risk, and that implies that we're in this section of the graph and not over here. Does that make sense?
I see. It was that area is centered on point 2.
I'm sorry?
The area of interest is centered on point 2.
I think he's talking while muted.
Oh.
You're muted, Robin.
Oh shit! Sorry, guys. So what I was trying to say is if a clinician is willing to conduct 20 biopsies to find one high-grade cancer, then that's 1 to 20, 1 out of 20, and that's 5%.
Yep.
So the probability threshold would be 5%. So that would be more like 0.5 over here.
Yes.
In
Okay.
that case. So it's 20 to 1. So here's the ratio. So it's like more 20 to 1. So it's like over here.
Okay. But it's still a range that you gave, right? How did you? Is that the bottom, the middle of that range?
Yeah. So this is the range. So this, in this case, because it's this type of cancer, Dr. Vickers told me. I made this chart with his software, and he told me that first I showed this one. He says this is silly because the only range that matters for this medical case situation is this range here. So you should zoom into that. This is the range that matters, and that is based on the clinician's knowledge.
Okay.
Any other questions? Okay, great. Robin, thank you so much for doing this.
Thank you.
And great presentation. And we're going to do a quick little changeover. Robin, if it's all right with you, I'm going to get us out of the Zoom meeting because I think there's some echoing. And you can follow along in the YouTube live stream. Make sense? All right. So yeah, one more round of applause. Yeah. All right.
Used to, not anymore.
Okay, just a show of hands. Who skis? Has anyone skied here ever?
Behind you, yes.
Okay.
By the way, take this lapel mic.
So, can you hear me? Yeah.
Okay, awesome, great. And I don't know, give me a hand signal if you want, and I can push down.
Okay.
That work?
All right. Okay, that works.
Let me just. Go ahead, give your intro.
Right. Hi, everyone. My name is Sumit Meghlani. I recently graduated from UBC in May, and I'm looking for a job currently. And I worked with Borealis AI over the summer, and this is it's my first E.A.D, age-aided detection, a fresh perspective on saving lives. So the purpose, Let's Solve It, is the program I was with. It's like a mentorship program with Borealis AI that connects me and my other fellow undergraduates with mentors and resources at Borealis AI in order to solve a community problem. What we decided to solve was SEM devices. SEM devices are satellite emergency messaging devices that backcountry skiers or anyone pursuing outdoor activities usually carry with them to communicate with the city or just to have a mode of communication. Sort of the background, there are 38 million head injuries, 12 million Sports related, about 600,000 deaths. And 1900 yearly incidents in BC, out of which around 2,000 people survived from like a few volunteers from 78 search and rescue groups in BC. This was during the winter. And so our approach, we have certain stakeholders. One is the alpinist that wants to travel light and fast. One is the search and rescue group that wants to know as much information as possible about the alpinist, where it is, and what state he's in, and safety about both of these agents, right? If they're going out into the wild, they need to be safe. So the current technology, the SEND devices, is that, like the prior technology was that once you press this SOS button, which is around here, after you remove the tag, it sends a signal to a satellite, and the satellite sends a signal to a monitoring agency. The monitoring agency then sends the alert to the respective authority that dispatches resources to you. Previously, there was only a GPS coordinate that was given, so you could only know there's help needed in this part. But now, with new technology, it's the InReach device that government has a monitoring agency and a subscription that whenever you press that SOS button, someone tries to contact you to learn more about what your situation is, and then send resources accordingly. But we thought of it, we thought like this could be done better. So we thought of using AI to resolve our issue. So the data that we were working with is that all skiers or any other activities you're doing, you're probably going to be wearing a helmet. And why the brain? So like everyone knows how a brain works here. Still, I just got a slide here just to be safe. And an easy way of putting it is think of each cell in your brain as called a neuron, like a tiny little floppy noodle that has an ability to generate like tiny little electric impulses. Your brain is essentially composed of 1,000 such noodles that send these impulses, right? And EEGs are basically sensors or way of detecting those impulses. This graph over here is about a subject that was viewing a movie that was showing some emotions, such as happy, sad, something. So you can see certain patterns around here. So for our data set, we had a data set on emotion and motion of the subject. The emotion data set was about 42 gigabytes, sampled at around 200 hertz. And motion data set was about 1.2 GB with sample around 500 hertz. The emotions were a lot, so I grouped them into three, which are most concerned with our research, which is fear, other, and neutral. Other emotions were such as happy, sad, disgust, that I didn't really need from analysis. And motion, there are about 6 ranges of emotion that I'll go into deeper. So this is the pipeline. Like I said, we had two data sets. I merged them together for the model because now it's like the EEG data that I have. I pre-processed it, so I selected 28 channels. 28 channels mean 28 senses, which are on the center part of the brain. Because I think my emotion data set had about 64, and grasp and depth had about 32. But the intersection between them was 38. And then I did the normal steps like resampling and standardizing and removing certain chunks. Then I took it into a model and evaluated and released my predictions for emotion and motion. The model, which is a CNN, you can think of it in like the most granular way. Is essentially we are scanning each of those waves that I showed you before, like with the detection, like and adding a score, like a probability score of what the person was feeling when he was doing a certain activity. CNN is just a mathematical way of systemizing that. Mathematical way of representing that spatial invariance. Hence, we decided to with fewer parameters. Hence, we decided to go with CNN because we were working with certain time constraint of just working with the sun. The results are as follows. For motion, we had an accuracy of 0.8, and the loss function was +3. For emotion, you can see it is quite variable. It was around 30%, 37%. Hence, the whole model training accuracy was quite variable when it was performing really well because the motion was performing really well, and then emotion was not performing to the same extent. So it was like really sporadic. You can see that. coming to the limitations, model accuracy could be improved by using multi-objective learning. There was a certain assumption that we made that if we can predict fear, this can extend to pain, which is essentially what we are looking for, because but we didn't obtain the data set on that end. And then since the subjects were different for emotion and motion, because there were two different data sets of taking two different separate trials, the analysis may not be as accurate. So the next steps for our research would be to develop a prototype like a helmet, then collect some real data, probably change the model using transformers that could help us infer more, because they work on fire and condition probabilities, the inference will be much quicker, and publish the research to improve the industry. Thank you. To conclude, we managed to develop a model that detected 3 emotions or 6 ranges of motion using brain waves this summer. That's it.
Great. All right.
Is that on time?
Yeah, you had 18 seconds left.
Yes.
Yeah, there you go. So I got a question from the chat here. So emotion data is actual data from an alpinist. How is that collected?
No, it is not data from the alpinist. Actually, I can speak more about the data set. Wait, how did you move this? Yeah. Speaking more about the data set on the emotion side, it's conducted as follows. So there were a certain amount of subjects, about 15 subjects, that they were asked to watch 15 film clips, and yada yada yada. But all these film clips had certain emotion they were labeled as certain emotions. And what you were doing is you were evaluating what their brainwaves were like when they were watching certain clips. That's how I got most of my emotion data. But also, like I suggested in the presentation before, there were certain emotions such as, I can't see this person, so I don't know if I'm answering the question, but like there were certain emotions such as happy, disgust, anger, which I've binned into other emotions because that's not something that we were associating our research with. And so we only had 3 emotions that we were mostly concerned with, which was fear, neutral, and other. But alpinist is something that we look forward to doing in the future.
Any questions in the room? Okay. I am?
You asked for it. Yeah, so I guess I'm wondering like why, like it seems like a really cool technology with lots of other applications too, but it seems like a bit of an overkill just to detect that someone is injured. Like why not monitor heart rate or perspiration or lots of other things? Like EEG seems like a very hard way of solving this problem.
Right, it is. You're right on that. And the reason I use EEG is mostly because, like I suggested before, the alpinist wants to travel light and fast, and one of the gears that they already carry is a helmet. Right? Anytime you're doing skiing, motorcycle, American football, any of these activities that you're really doing, you're always wearing a helmet. So I was thinking, like nowadays, portable EEG headsets are common, so you could generally use EEGs for that. And thinking about the perspiration and heart rate sensors, those could be also used in conjunction, right? That would improve the accuracy of our model. So yes, we did think about those strategies as well. But for our research, we were mostly concerned with EEGs because we had to decide for our research problem in those short span of 2 months.
Anyone else? Dan.
So one thing that's tricky about this is evaluating it in the real world. Because before you use it, you want to trust it that it has been evaluated. So how do you go about
evaluating?
Yeah, bridging that gap between like taking it out of the lab and using it.
Right. So from doing a bit of research on the neuropsychology side of things, so as an experiment, you can't really hurt the subject, right? So one of the things that they're trying to evaluate, they're trying to reduce this deaths through avalanche, right? That's what kills when skiers out there in DC at least. So what I'm thinking is one of the experiments that you could do is place a hand of the subject in ice cold water, and that's going to affect pain. Certainly, and what are the brain waves going to be associated with that? And then use those, train the model on that, and then apply it to others to see if it can detect that. create emotions that distress. And hence you can use it in like a real life situation. And then there will be some certain testimonial, certain industry measures that I'm not aware of it yet, but I'm pretty sure that they should pass this. Does that answer your question?
Yeah.
Okay.
Go for it.
Yes.
So, does generalize well for people that were not in the training set? Like if you train half of the, like 8 people, how well can you do half of the 7 people?
I'm sorry, I didn't quite get that. Generalized on like, are you suggesting that, okay, I've done this test on certain subjects, does it generalize enough for the whole general population?
Yeah, like if you test it
That's the thing, I did not have data, and that's one of our next steps to test it on. For the data set that I had available, the subjects were different, right? Because I was looking at, I had an emotion data set and an emotion data set, and I was fusing those data sets together and trying to predict it from my model. So in that sense, what I was trying to, the underlying assumption was that everyone's brain sort of has the same impulses that it generates, and I should be able to predict using my model what they're feeling, which may not be the case in real life if I was to test it, but we didn't have that data available because there was no experiment done to this state where they go into like they're running and they are putting their hands in the water at the same time. So we have to work on what to do with it. Does that make sense? Does that answer your question? Sort of?
I think he's also asking about, like, did you have a validation set?
A validation set?
Yeah.
Okay, for our validation set, what we did was, like I said, that's a really good question. And I don't have it on the slides, but I can explain it. So my seed data set, I had a bunch of trials that happened, right? So I take let's assume there are 3 trials. I took 2 of those trials to train on, and the last trial to validate my set, or validate my research on. But for my grasp and lift, the motion data set, the 1 GB of it, I only had the training set, so I had very less data set to work with on that end. So what I did was when I tested, of course, my results from this training on the emotion side of things, I realized that I was getting an accuracy of around 136, but on my motion side, I was getting an accuracy of 80%. So I decided that not to, validate it because I thought that it would be similar or much less. Because what I want to validate it on is like using motion and emotion. But so I decided that it might be more fruitful to try a different model or try getting a better data set before validating it on the motion side. So I increased the data set. So I kind of like fixed the data imbalances before I tried to go validating it.
We just got one more comment here. Great work, just commenting on the emotions of alpinists works differently. Speaking from personal experience, I can probably talk whole hours about the situations where it needs to work. There needs to be a good characterization of the situation linked to EEGs before making predictions. Feel free to reach out to me if needed, and I'll give you like his contact information. But yeah, that is a good point because supposedly someone who is seeking out danger may have a different response to stress from a typical person.
Right.
Yeah. Any other questions? We might have time for one more. Well, then I'm going to use it. I'm just more curious about your. So you have the 2 data sets and you have the 2 objectives, and I'm just curious about what you learned ultimately from trying to fuse these data sets together. Would you do it in the future? And if so, would there be anything else that you would try? What worked, what didn't?
Fusing those 2 data sets was a very unique task in the sense that because I wanted my model to kind of predict on these 2 ends, right? Emotion and motion. But one of the data sets was sampled at frequency of 200 Hz, the other one was 500 Hz, and it was really hard. It was really, I guess, the truth of the statement is that it was very hard to evaluate the model in that sense. How would I go on evaluating this model? Because one of them is a binary cross entropy the other one is cross-interactive. How do I optimize it using the same model, right? And I used a different approach where I was changing the iterative between, like every 20 iterations between optimizing on one objective and many other. But there are many other, I looked into the research, there's multi-objective learning that I could have used, which is essentially adding auxiliary loss and then optimizing on it, which could have improved the model a little bit, or maybe change the whole structure and using transformers that could have probably improved on it. So I guess like I really enjoyed like it was grueling to work with it, but I feel like it's very applicable and there are many applications of this methods that I should look into it deeper and probably increase my skill set in this. And yeah, so I would use it in the future to answer your question, probably in a better sense, using something like multi-objective or transformers.
Sounds good. And that's all the time that we have. Do you mind taking off your mic? And
Yeah.
Bill, you're next. Okay, awesome. So just start, and I'll start timing, and I might flash some numbers in front of your face.
Okay, thanks. Hi, everyone. My name's Bill Tubbs, and I'm going to present on smoothing a signal. So what is smoothing, and why do we do it? Often our data is corrupted with noise, and we want to remove that noise so that we can get at the underlying signal underneath the data. And in the case of a time series, we're talking about data that's spread over time. So on the x-axis, we've got time, and we want to estimate the true value of y. So here's an example, a sample of data. How would we smooth this? What would you consider to be a good function smoothing this? Would it be, for example, a straight line, or maybe a gradual curve, or should the line in fact go through every single point perhaps? So here are two curves fitted to the data. How would you determine which is best? I think the answer is it's impossible to know without more information. We have to ask, where is this data coming from? What is the system that generated this data? What do I know about that system? Only by answering those questions can we decide which of these curves most likely represents the true output, y. So for example, if I told you that this data is the temperature in a river every hour, then you might decide, okay, well, in that case, the orange line is the best estimate because I know that the temperature in this river can only change slowly. If you know something about rivers, maybe you decide that. On the other hand, if I said this data is the temperature of the wastewater coming out of an apartment building in the morning, you might say, oh, actually, that can change quite quickly. People turn on showers, turn off things. So, this yellow line is probably the best fit. So the point I'm making here is that to smooth the data, we need some kind of model of the system. And whether you specify that model explicitly or you're just using your instinct, either way, you're making assumptions about what the true system is. So why not specify that model explicitly in order to do the smoothing? So now I want to consider a slightly different problem, which is slightly more difficult, and that is online estimating. So this is when we're making decisions in real time based on the data as we receive it. And this is the case when you want to control the system, because then you need a good estimate of the current state of the system so that you can, ideally without any measurement noise, so that you can make a good decision and therefore control the system. And so in this example here, we've got these data points and this new data point comes in. What is the best estimate of the current state of the system? It looks like it's higher, right? The latest measurement is higher. Or is that just a measurement error? Is that an outlier? And actually the system is down here. So it's impossible to answer the question, but this naturally leads to a Bayesian approach. We can estimate the probability distribution of our estimate, and we can pick the most probable estimate. And then every time we get a new piece of data, we can update our probability model and thus produce the best estimate of the system at the current time t. But first we need that model of the system. And so this is the general structure of a model that we would use for state estimation. It has three main components. The system model is a dynamic model of the system, which defines how it responds to inputs. And there are two main types of inputs. There are known inputs and disturbances. And known inputs are, for example, if we have manipulatable variables in the system, then we can include those in the model. And everything else that we don't measure is a disturbance. But just because we don't measure it doesn't mean that we don't know anything about it. If we know something about the disturbance, we can incorporate that as a disturbance model and also include that in our model. And finally, we need a measurement model, so some kind of model of that noise that we think is causing the measurement noise. And that's easier to estimate usually because we can see that measurement noise directly in the output. So by defining the three components of this model, we're specifying our beliefs about the behavior of the true system. And now we can use that model to interpret the data, and we do that with a Kalman filter. So the way a Kalman filter works is it takes the available information, the measurement, and any known inputs, and it makes a prediction using the system model of the output. And that prediction is then compared to the measurement, and the error is then transformed into a correction to the models. And that happens each time step. The correction gain, K, is a tuning parameter. So if you know that the measurement noise is low and the disturbances are large, then you're going to set a high gain, and that means that the model and the predictions will adjust quickly to the changes. But if the measurement noise is high, then you're going to set a low gain, and that means that the predictions will change slowly, smoothing the signal. So back to that original data set, here is the output of a Kalman filter. So in orange, you can see the estimates of the Kalman filter. And the yellow line is the actual true system output, which I happen to know because I simulated this system myself and added the data. So I know the true output. And as you can see, the Kalman filter tracks the estimate, and it even takes account of a change in the known input that occurred at this point here. So that's that. And one interesting observation, people who've studied the brain say that there is a two-way flow of information in the visual cortex where we process signals from our eyes. Sensory data from the eyes comes in at the bottom and flows up through the hierarchy. And the predictions come down towards the sensors. So I'm asking the question, maybe we're actually using a Kalman filter. Thank you.
Nice, right on time.
That was close.
So, yeah, questions in the chat. Does anyone want to start? I have one. I have a bunch, actually. So, if you could go back to that previous slide. One the other way. Yeah, that one right there. What I kind of see from the way that you simulated this is sort of like piecewise, right? And I'm wondering if the Kalman filter can also do any sort of change point analysis as well.
What was the last bit?
Oh, I'm just wondering if people use Kalman filters for change point analysis. So detecting when, say, the distribution has shifted like quite rapidly in a given time.
I don't know what change point analysis is, but based on what you just said, there are two types of Kalman filter. There's a steady state version and a dynamic version. The dynamic version can adjust to the changes in the amount of disturbances and noise. So maybe that answers the question, but I'm not actually sure what the question was.
Anyone else? Yes.
While we are on this graph, I guess I'm a little bit surprised, like when you get the first point that's outside of those first cluster, the model gets it so quickly. If it was Bayesian, you might wait for the next one to update the prediction. How did it do so well?
It would have been a tuning thing, and also a bit of luck, because if you notice, the measurement is slightly higher than the true system. But so I've probably set the gain a little high here, and you can see that the predictions are a little bit noisy. If I turned down the gain, this would be smoother, but probably there would be a delay there reacting to the change. But a good question.
Andrew? So you're talking about the tuning parameter K and how fast it would learn and how that would affect things here. Do you have like a rigorous method of actually coming to the right K?
Yes, I don't, but Kalman did, and that's why it's called the Kalman filter. But you have to make a lot of assumptions. So if you have to assume that your model is linear, your measurement noise is Gaussian, and the noises driving your disturbances are also Gaussian. If you do that, and if you have a perfect model, then there's an equation, it's called the Riccati equation, which will calculate K.
Those are pretty strong assumptions, though.
Strong assumptions, yeah, exactly. So none of those assumptions apply in reality perfectly, and so a Kalman filter is always approximating. It's never an optimal estimate unless all those assumptions apply. But in practice, it works very well. I mean, it's used extensively in control engineering for state estimation. One at the back.
Yeah, question. So going with the Bayesian model, does it make sense to put the prior over K and then just kind of learn the proper value for K?
Learn K. That's a good one. I'd have to think about that. So that would be like an adaptive Kalman filter. I think it's similar to your question, and I don't know the answer.
Got another one?
Yeah.
So, like when you actually have a Kalman filter here, you talked about it being Gaussian noise, right? And I assume that's just to get that equation to pop out, right? Because it has nice properties. Can you replace that with, say, some sort of heavy Kell distribution like student T or something like that?
Yep, there's lots of innovations on the Kalman filter. So there's an extended Kalman filter, and then you can go even further into particle filtering, and they don't rely on these assumptions. So you can have any distribution. Obviously, then it's more of a numerical approximation, but you can program all kinds of distributions in. And back to your question, it just dawned on me. In the dynamic version of the Kalman filter, K does vary over time. So you're updating K as well based on the measurements. Any questions in the chat?
Someone is typing a question. So while we're on the subject, so let's say we're talking about this like wastewater treatment type situation. If I was managing multiple apartments, how would I share information like between like these different measures that we are thinking are coming from a similar distribution but are not the same distribution?
Yeah, so that's a good question. I mean, you still need a model, so you would probably maybe using first principles or some data, come up with a model for one apartment, and then when you translate that to another apartment, you obviously want to allow the parameters to change because one apartment might behave slightly differently. So maybe you could find a common model structure that works for all apartments, and then it's called system identification when you identify your model, and then you would tune the model to the specific apartment, and hopefully that would be the best of both worlds, right? You're not making a unique model for every apartment, but you're also adapting it to its behavior.
And a question from the chat here. Can you please explain the difference in the static and dynamic version of your flowchart, and what components are different?
Well, that's a big question. I deliberately left all the equations off this, but there are equations. There's a Q matrix, which is a covariance matrix of your disturbances, and there's an R matrix, which is the covariance of your measurements. And using those, you can update K every time step. So the equations are surprisingly simple, but I haven't got them here. But you can look them up. They're on Wikipedia, and you can update K every time step, and then you use K once to update your model, and then you recalculate K the next time step. It's a recursive procedure. It's not computationally intensive. It's widely used and well known.
I'm wondering if, like, the system level itself might have some parameters, like the choice of the song, like the lambda or whatever. Like, can you do similar things? Like, you have a static model and a dynamic model version of Kalman filters?
Yeah, that I don't know actually. I mean, that would be adaptive control, and I assume I know in adaptive control they're adjusting the parameters of the model. So if they're using a Kalman filter, it's the same model. You use the same model for the Kalman filter that you use for the controller. So I don't see why not. Maybe the catch is that you're also using the model to estimate the states. So yeah, you might be doing the circular argument, but I haven't done that. But I think that would be possible. But in generally, control engineers don't do that. They get a bunch of data, they estimate the model, including the parameters from the data, and then they freeze it. There is a field called adaptive control, but very few controllers in the real world are adapting. It's too risky. People don't trust it.
I think that's it. Thank you once again, Bill.
No problem.
For the talk. And Nicole, if you could grab that, and if you could do the presentation behind the laptop. Okay, last talk, then food, possibly beers. Nicole, do you want to introduce yourself?
Yes,
I'll be
sure.
making hand signals towards you.
Okay. Hi, everyone. It's great to see you all in person. And thank you, Learn Data Science, once again, for giving me this opportunity to speak at Lightning Talk event.
We are going to need.
Okay,
Yeah.
sorry. Oh, I cannot yell. So.
If you kind of just like stay nearby and put this on your lapel, that should be fine.
Okay.
Yeah, so just don't walk around too much.
Can everybody hear me better? Is that okay? So this.
Is it working?
I think it's just I guess my voice is not very high. Sorry, hi. So it's great to see you all in person again. My name is Nicole, and I work as a data scientist at software development company called Many Hat Software in Vancouver. I will be speaking about machine learning for insightful search engine today, but this title could be a little misleading because I will mainly talk about the search engine fundamental and models involved. That does not mean that there is no machine learning component. There will be some. I selected this topic because I was involved in the initial phase of the search engine design as one of my company projects. And also, there is a growing demand for a search engineer for building commercial or corporate search engine. And I'm not a search engineer myself, by the way, and do not have engineering background at all. So a lot of contents of this presentation came from my research and self-study. And I also refer to search engine course taught at graduate program in management engineering at University of Waterloo, as well as a number of other research papers. So I hope that I can still provide you with some insight about search engine. Also, search engine is a rather challenging topic to talk about in 7 minutes because it is very complex and intricate system where each functioning body in a search engine system requires at least an hour of talk. So I had to compress or cut down a lot of contents by focusing on fundamental of the system. So without further ado, let's move on. As a brief glimpse at the history of the search engine, the idea of using computers to search for relevant piece of information was popularized in the article As We May Think by Vannevar Bush in 1945. This article was published in Atlantic Monthly, and in 1950s and 1960s, the first automated information retrieval system were introduced. So what is search engine? The search engine is classified within the umbrella of information retrieval system, and within this IR system, search engine represents the practical application of information retrieval technique to large-scale text collection. The circle in this diagram shows 4 main IR applications that process various contents and execute tasks. And when we combine these 4 applications with unstructured information management architecture, or UIMA, along with the design and configuration components, it becomes a search engine system. The purpose of search engine is to serve as a fundamental tool and technology to help people better satisfy their information needs. And the information needs are unique for individual. Whether the query result is correct or not, the relevance of the information is entirely up to the users conducting the search. And there are many factors that affect person's decision when determining whether a particular document is relevant or not. And these elements should not be reflected in the language model algorithm for comparing tags or ranking documents. Overall, the search engine should help people solve economic and complex problems in their lives. So how can we build a search engine? By looking at this simple process, it looks as if everyone can build one's own search engine. There is a proverb saying, don't be deceived by the look, but it is actually possible. And each step in this process diagram represents the basic building block of search engine architecture. The overall fundamental architecture of search engine looks something like this. The core component in this architecture are the index engine and query engine. The middle layer with components in green color is like the brain of the search engine, where the most language models are constructed. Optimization is done by evaluation process for better user experience, and this process is crucial for search engine design. The process involves both human participants and computer-generated simulation in the online field evaluation and offline user studies. The field evaluation involves a dynamic, real-time, continuous web feed and the online usage log with the records of user interaction with the user interface of the search engine. The online usage log is further processed to calculate the up and down movement of click-through rates to measure the quality of online search. And in offline studies, human participants can be given task A and B, and the same tasks are simulated by computers to measure what we think the quality as perceived by human would actually be. The ultimate goal is to see if the document is useful and relevant to the user, and what those sets of documents are. And the response to this question impacts the ranking system. So when we say language models in search engine, it refers to models that are based on probabilities. And not all, but some of these language models are machine learning models. And for the next few slides, I will talk about language models for scoring, ranking, and query function. This diagram introduces the basic concepts of the IR model by integrating different views of computer science and other related fields into 4 distinct views. The basic concept is that when we want to perform the information retrieval on documents, we have to consider all of these 4 views either independently or in combination. 3 most basic models with ranking and scoring algorithm are TF-IDF, BM25, and SBERT. To illustrate, I built the algorithm of these models and tested on the 4 text samples B, C, E, and G. And based on the simple query banana, B, C, and G are related to one another, where yellow fruit in the sample G implies banana. When looking at scores, BM25 scores are higher than TF-IDF, which show that BM25 optimizes TF-IDF to capture more semantic context. But both TF-IDF and BM25 fail to notice the sample G. SBERT scores imply that SBERT can capture the similar semantic term in the sample G and can associate sample G with sample B and C. For a search engine to classify a document as relevant or non-relevant, the conditional probabilities for each classification needs to be computed. The question is how. This can be answered by relevance and retrieval model. Relevance model is query language model that represents a topic covered by relevant documents. By taking the probabilistic approach based on the concept of relevance model, the ranking algorithm can be formulated in these 4 steps, and each of these steps provide answers to the relevance question as illustrated on this slide. And the probability formula derived in the end represent the relevance model. The classical retrieval models are based on propositional logic, and this model cannot properly deal with spatial relationships. For example, in an image with tree and house, the propositional logic can only represent the fact that there is a tree and house, but it cannot represent their spatial position. So the model requires binary predicates in order to deal with spatial relationship. Terminological logic is IR model based on the predicate logic, and modules under this model have the elements that define and control the structure and syntax of terms related to spatial position in the document's inquiry formulation. The current most advanced search engine systems are based on the fundamental architecture and model discussed so far, and also with the incorporation of deep learning models. The primary examples are Microsoft Neural Search Engine and Amazon Alexa, the voice-activated interface. And my apology for going through this slide very quickly, but this is the architectural review of the mini language model developed by Microsoft Research in 2020. And this is the architectural review of Amazon Alexa empowered by AI and Internet of Things. To wrap up, I would like to conclude by mentioning the impact of search engine in the context of research paper that studied the positive and negative influence of search results on people's decision about the efficacy of medical treatment. This research was conducted by University of Waterloo, and there were 3 main things that the researchers found from this study, which are stated in this slide. To sum up these 3 points, because search engine plays a significant part of shaping our thoughts and belief, the search engine design should meet its purpose and quality standard that does not result in harmful search. So this concludes my presentation. Thank you very much for listening, and I will now open the floor to questions.
All right. Starting that. I'll ask the first question. What is BM25?
BM25 is derived from TF-IDF. So it is a TF-IDF, and it has the same algorithm, but it has also additional tuning parameters, which is saturating the output produced from TF-IDF. And there are 2 other constant value, which are sort of serving as a weight. So it, based on the algorithm, it optimizes TF-IDF, and because of that, it can capture more semantic context in comparison to TF-IDF. And then I think it was introduced a while ago, but we are still using BM25.
You showed a couple of models from actual companies that run search engines. To what extent do they share how they work? Is it secret, or is it all available for scrutiny?
So Microsoft, sorry, I can't pronounce very well, sorry about that. The Microsoft Neural Search Engine, they have actually their own conference. They have been providing their talk on how their search engine works and how it should be improved. And then I got this diagram from one of their conference talk as well. And then they produce constantly like a research paper every year. So it's not secret to the public, actually. So it's great that they are sharing their architecture of the search engine. Probably not the commercial secret, but like the actual the model, how the model works, it's been actually shared.
I have a similar flavor of question. Like I'm trying to get a sense for what's the most difficult part of starting a company, building a new search engine that's better. If it's not the algorithm, they're just sharing it. Is it the indexing? Do you need a lot of infrastructure? Like, what do you need? What is the hardest part of creating a better search engine?
It goes very back to the earlier slide, and also there are some slides I didn't get to share to talk about more aspect of that side of things. So search engine actually its relevance is important, but actually it's more than that. It's more than satisfying people's information needs. So if we look at the search engine algorithmically, it's really hard to know how we are satisfying people's need, because individual needs and demands are very different, even though they are looking at the same. So like, for example, they input query to search engine and they get the documents which is ranked in the order. But then not everybody will be happy with those contents. Some of them, they already looked at it before, so they wouldn't think that that's really good, the search result, whereas other people satisfy it. So that's number one. We don't know what individual needs are. And then another thing is, because this is not 100% perfect system, so it could lead to the negative search result. For example, it will produce inaccurate search results. That could be very harmful because it can, again, undo the value of search, the correct search, accurate search. So then that can be very harmful as well. So then the company needs to deal with that. And then all of this can be improved by doing the evaluation process, which will optimize the search engine, which I mentioned earlier. So if I go back to the earlier slide, where I talk about the optimization. So this process where company tries to capture, actually this is done by research group, but a lot of companies follow this process as well. So they have in-field evaluation, and whereas they also have offline user study as a research and development. And then they do this by observing what people look at and how they behave by installing their live system, where they constantly measure how people behave. So how many times they click on certain sites, how much time they spend on certain search the result that they pulled from the document, and also what they look at. So they also look at which side of the screen they look at, and I don't know how they capture it, but they also capture those. Everything is logged into the usage log on this diagram. And then that's further processed by their live system to calculate a lot of things. And also they interact. So they actually contact the person who actually did that search and then ask them, okay, why did you spend that much time? Why did you get to click that many times? Something like that. And then they get a further insight. And then they implement that for their ranking algorithm, scoring algorithm, and other part of the search engine. And then that is really expensive and very time-consuming study. So a lot of it is also done by offline user studies, where they do work with the human participants I mentioned earlier, and they also do the computer simulation study as well. And then they compare the results, and then they analyze the results to constantly improve the search engine system. So there's a lot of things actually happening behind the background that we don't know. But a lot of it is like a probabilistic approach, and also statistically driven algorithm. And then there's deep learning and transformer machine learning models in play as well. Sorry, I hope I answered your question.
Any other questions? I think we're good. One more round of applause for Nicole. Thank you, everyone, for coming out. For those of you in person, our reservation is at 8. So if someone can go to Library Square right now and say that that we are going to be there, that would be super great. For those of you who are online, thank you so much for coming and viewing. And we will have an archived version of this stream. And we hope to see you sometime soon. I am going to exit out